discuss about a very important factor here, which is kinetic molecular theory. So, what is kinetic molecular theory? Or we will discuss the postulate which was corrected by Wonderful that was given by kinetic that was given in kinetic molecular theory. So now I'm going to discuss about the Wonderful equation, or which is also known as Green gas equation. Actually, Wonderful corrected the two postulates which was given in the kinetic molecular theory. The first was gas particle particles do not attract or repel each other, right? So there's no force of attraction acting between them. And the second important postulate was that gas particles have no volume. They have negligible volume. So Wonderful corrected the two things. One was volume and the other was pressure. So now I'm going to discuss about the one factor, which is first of all I'm going to discuss about the volume. So volume of first of all the volume of real. Wait. I've got in here notes, but I don't need it. Right. So okay, wait. Let me just get it again. Okay, so let's get it again. Okay, right. So first of all, I'm going to talk about the ideal volume. Ideal gas volume. Here, right. So we can consider. Let me just. So we can consider the two containers here. Right. This is one container. I'm so sorry. These are the two containers here, right? So here you can see that the gas molecules are spread all over the container. They are point masses, right? But if we see the pressure, and here we have collected all the gas molecules, the volume is negligible, which means we always take the volume of the gas is equal to volume of the container. Volume of the gas is always equal to the volume of the container, right? Volume of the container. I'm getting a little bit difficult to write it, so I can write it with the help of this. Volume of gas is equal to the volume of container. In the ideal gas, I'm talking about volume of gas and volume of container. We don't neglect this part. This part we should just, because it's also occupying the space, so we have to neglect it. But what happens in the real gas equations? First of all, we have two containers here. One container, second container. First, and the one thing that we need to remember here is that the real gases have rigid spheres, share of large masses, right? Oh my god. So if we collect them by increasing pressure, we compress them here. We can see that total pressure, I'm going to write here the total volume total volume is equals to volume of gas minus volume of container, right? Okay, so mathematically we can write that EV is equal to V, capital V, small t is equals to volume of container I'm trying to get it plus B. So B is basically a constant here. So which is also known as B is a constant, which is wonderful constant and also known as excluded volume. High volume factor, cofactor, and a lot of other names. So B is basically an excluded volume, and it is a volume of volume of the container. Volume of container. Right. For example, we can understand it with the help of an example. For example, the same example, two containers. This is something like this. We have molecules spread all over the container. You have large size. But if we just compressed it, so we have to neglect this space, right? Where we have compressed all the molecules because it's overflowing space, right? So we have to neglect this volume to consider the rest of the volume. Sorry, the rest of the volume of the container, right? What's volume? Volume is basically a free space where the gas can occupy. Uh, Gas can easily spread off the occupied space, right? So B is excluded volume. Now I'm going to talk about the significance of B and the unit of B, right? So for that we need to move down. Let's move down. Wait, I guess it's fine. So I need to read this stick notes immediately. So what is B? What is significance of B, right? So I'm gonna write the significance of B. Significance of B, right? Significance of B. So B is directly proportional if I'm writing the short form here, directly proportional to size of the molecule. Size of molecules, right? The more the bigger the size of the molecule, the more space it occupies, right? For example, something like this. This is another container here again. This is only a rough diagram of container. This is something like this container. So these are the very large masses, the point masses. So this, for example, I have compressed at the high pressure. The molecules are here. So I'm going to neglect this volume. The larger the size, the more the volume we need, right? So what is the unit of B, right? What is the unit of B? So we know that the B is equals to B minus, remember that we are talking only about the 1 mole. So that's why I'm including NB. So let me just write it here as well so that you can write your points that we only discuss 1 mole here. We are only discussing in terms of 1 mole. In terms of 1 mole, right? No more than that. 1 mole. So V minus NB. We know that the V, this is V. I'm sorry, I might have mistaken here. This, I'm going to write this equation here again so that might be confusing for you. This V is equals to, volume is equals to V minus NB. This is volume, right? So we know that the same ratio VV. So the unit will be something that is Pm cube per mole. Or we can write it like this as well. Pm cube mole minus 1. So we can consider this is mole minus 1. So this is basically a unit of the P. B is basically the excluded volume or cofactor or the constant of the, do you know what's the equation here? So I'm only writing the equation here of van der Waal, right? Which is nRT, but as we are talking about only 1 mole, so there is no need to write n here just because 1 mole, 1 multiplied by RT is equals to bracket. Oh, I'm getting difficult getting the bracket here. Wait for a while. Yeah, it is P plus an square divided P plus an square divided by v square. Now closing the bracket here, and again we know we need bracket here, P minus nb, and again closing the bracket. So this is basically a equation which is real gas equation. So this means, this part means correction in pressure that I'm writing here, and this part means correction in volume. Let's write it here. correction in volume. And the second one is correction in correction. Sorry, I'm doing yeah, spelling mistakes here, but that can ignore, right? Correction in the first. This one is I might have mistaken here, so you can shuffle it, no problem. There is correction in volume, and this is correction in pressure. Okay, so I don't think so I need to write it again. So this is the basic concept about the correction of the volume of the ideal gases, which was the two syllabus given by kinetic molecular theory. One of them we have corrected here. The rest, the other one that I'll be talking on the next video, right?